Good day, everybody. Today we're going to be looking at sound waves and how this specific type of wave behaves when we put it under certain circumstances, and what we can learn about how human hearing works because of how sound waves work. So if you go ahead and kind of follow along, we'll be breaking this down into three main kind of sections for this lecture. The first one is we're going to go over kind of the basics of sound waves and how sound is perceived by the brain. Then we'll talk about human hearing specifically and kind of the range of sounds that people are able to hear. And then we'll take a look at the speed of sound and what changes about the speed of sound given what it's moving through. So to kind of start off with things, we're going to go over just some basic things that talk about sound waves and specifically what it means for volume and pitch. And so for us to really kind of get this, we have to understand what sound waves are. So sound waves are mechanical waves, meaning they are physically vibrating the air or whatever they are moving through, and it's broadcast through a medium from one location to another. At this point, you've seen the idea of a medium before, and so sound waves have to have a medium to travel through. And so if I've got a tuning fork over here at the bottom, if I was to strike that tuning fork, it would create areas where I'd have a high compression of sound waves, and then I would have some areas where the sound wave gets more stretched out, and those would be my rarefactions. So I get another compression, another rarefaction, another compression, so on and so forth. And that alternating pattern of compressed waves and stretched out waves is what we understand to be sound. So in the case of sound, the medium is going to wind up being air, typically. You can hear sound through other things. And that's going to be kind of the thing that's being vibrated by those sound waves as it moves through. Now, there's a couple of things that just kind of basic understanding of sound waves that we need to have. And the first one is that sound is going to be a longitudinal wave. So kind of like in the example that I gave above, it's made up of areas where we have compressions and we have rarefactions. The vibration and the direction in which the wave travels are parallel, which means the vibrations and the waves are going in the same direction. So if sound is traveling from me to you, the vibrations in the air are traveling from me to you. And we can view sound waves on a tool called an oscilloscope. You won't need to use an oscilloscope for the sake of this class, but you might see it referenced in a test question. So an oscilloscope is the tool that we use to kind of visualize sound waves. Now, if we want to describe how we're perceiving sound, we might talk about something like how loud the sound is. So loudness of a sound wave is directly related to the amplitude of the sound wave or the tallness of that wave. And so you can see in the example, I've got the red wave, which is quiet. It's fairly small. And if I was to draw in kind of a midline for this wave, it would look like that. And so my amplitude, again, is the distance from the top or the bottom of a wave to that middle line. And so this being my amplitude A, if it's a relatively small amplitude, it's going to be a quieter noise. If I do the exact same thing with my blue wave over here, I'm going to jot in kind of a midline here. If I was to measure this amplitude from the top or from the midline to the top or bottom, this amplitude is much larger than the one for red, and so this would be a louder sound. And so when you are creating a loud sound, what you're really doing is you're creating a wave with a greater amplitude. Those particles are vibrating much more than they were in a low amplitude setting. So that's loudness. Now, the other thing that we associate with noise or sound in general is something called pitch. And so pitch talks about the musical note or kind of the high or low sound of the thing that you're listening to. And that has to do with the wavelength or how stretched or compressed the wave is. So you can see over on the left, I've got an example of a low pitch sound. This has a very, very long wavelength. Okay, if I was to measure from peak to peak or trough to trough, like I said, this would be my wavelength, or what we call lambda in this case. That's a fairly lengthy one compared to this blue one over here, where if I was to measure its wavelength, it would be only that big. So this would be a low pitch. It has a long wavelength. This is a high pitch sound. This is going to be a short wavelength. And you'll notice that between the two examples, they have basically the same amplitude. So these two sounds are going to have the same volume, but you'll hear one as being a very low sound, kind of a bass note, if you will, and the other one's going to be a much higher sound, a treble note, if you will. So those are the kind of the two factors about how we shape a wave and how that affects the way that we perceive it or hear it. So we've got loudness and we have pitch. So kind of moving on with that one, I've got just a quick question I'd like you to answer. Describe the frequency and amplitude of a high-pitched and loud sound. If you had to draw a wave to represent high pitch and loud, what would that look like? Now, the second section that we're going to take a look at specifically is human hearing. And the only real important part about human hearing that you need to know is the range of human hearing, because there are sounds that we can hear, and then there are vibrations that our ears are simply not equipped to pick up, but other animals can. Like dogs and cats are able to hear things that we can't. That's why dog whistles work. So human hearing falls between this range of numbers. It goes anywhere between 20 hertz, which is the lowest sound a human can hear, and so this would be a low frequency, and 20,000 hertz or 20 kilohertz. This is the highest sound that humans can hear. Sounds do exist that are higher than this, but we call them ultrasonic because we can't hear them. But there are a lot of animals that can. Again, hearing a dog whistle is a great example of an ultrasonic sound, something that we can't hear, but it is still a sound to other things. Now, can you hear 20,000 hertz? No. No, you can't, because over our lives, we get hearing damage, and that slowly reduces these numbers, or I should say, it kind of shrinks the range of your hearing, the more hearing loss that you have. So if you're frequently around really loud noises, or if you're frequently kind of listening to your headphones way too loud, or you're next to cars or jet engines or whatever, you can receive hearing damage, and that's going to reduce the range that you're able to hear things. Now, for the most part, most people would never notice because it takes away from from the range of sounds that you probably aren't paying attention to much anyway. 20,000 hertz would be extremely high-pitched. But it is worth knowing, and you can do hearing tests to kind of figure out what is your personal range of hearing. So you should know these two numbers. So if there's something to highlight here, I would go for the 20 hertz and the 20,000 hertz. Anything in between these range, again, this could be also 20 kilohertz. Anything between this range is going to be something that humans could potentially hear. And then our last topic to look at is going to be the speed of sound. So we're comparing and contrasting some transverse and longitudinal waves here, but mostly we need to understand the role of the medium when it comes to the speed of sound. And so the speed of sound is defined by whatever it's going through. So sound doesn't have a constant speed. Like we can talk about light as if it has a constant speed. Sound does not have a constant speed. Its speed changes based on what it's moving through. And so we've got three potential mediums if I kind of group things up. We've got solids, we've got liquids, and we've got gases. Solids transmit sound the fastest because those particles are really close together, so when one of them starts to vibrate, it starts knocking the other ones around. Liquids, kind of thinking back to when we talked about states of matter, liquids, the particles are a little bit more spread out. So they transmit sounds a little bit slower because those particles have to move more before they run into something else. And then gases transmit sound the slowest. It's actually the worst way to transmit sound is through a gas. And so you can kind of do experiments with this. If I was to put you on the opposite side of a very, very long steel beam and hit that beam with a hammer, you would hear it through the steel beam before you would hear it through the air. You would actually hear the exact same sound twice because solids transmit sound so much faster than gases do. And it's worth noting that sound has to have a medium, which means if you don't have a medium, like if there's a vacuum and we've taken all the air out of something, sound can't travel through that. This was the movie poster for the 1979 movie Alien, which they still come out with alien movies occasionally. And the poster said, "In space, no one can hear you scream," and that's 100% true. You would see the person's lips moving, but if there's nothing for the sound wave to travel through, there won't be any sound. So those are kind of the things that you need to know about sound waves. For the very end of your notes, I'm going to ask you to summarize with 6 different questions here, and I've got those questions up on the screen. Include those in your notes, please, and have a great day.